Hey folks, hope you're doing well. Today we're going to focus on chapter 25 and knock out the balance chapter. Again, we kind of already finished talking about digestion and absorption, getting these fluids and ions and things in. And then we talked about metabolism. And through the process of metabolism, we're going to create waste. We kind of talked about how we're going to remove that waste from the kidneys in our previous chapter dealing with urinary. But now we're going to talk about how we balance these things in the blood, kind of before we even get it to the urinary system. So this is chapter 5. We're going to see that this is about balances overall, fluid and electrolyte balance, and acid base balance. When we take a look, we do have three main balances we are focusing on: fluid, electrolyte, and acid base. But the fluid and the electrolytes help balance each other out. And so their goal combined is to help maintain the volume, the total amount, and the composition, the electrolytes, the ions of the extracellular and the intracellular fluid. We're going to get into this in just a second and talk about what is extracellular and what is intracellular fluid and what's going on in there, what electrolytes are more common. And so we're going to kind of focus on these two together as one group. And then as a separate group, we're going to take a look at acid-base balance. And of course, acid-base balance is talking about pH. So here we're going to talk about buffers. How do we buffer in the body? We're not going to get into the chemistry of buffering. We're just going to talk about what are the different buffers in the body. So fluids of the body first, let's talk about that. So the human body is between 45 and 75% fluid. And so when we look at that fluid, it all depends on how old you are. The younger you are, the more fluid you have in your body. The older you are, the more dehydrated we become. So younger, more 75%, and older is going to be more 45%. Also, adipose versus skeletal muscle, because adipose is storing a type of fluid, then we consider it to be more fluid based compared to a muscle. So if you have more adipose compared to more muscle, then you're going to be a bigger percent fluid, right? So it's not like you win if you have more fluid or anything. It's just kind of, this is what really determines the overall balance in the human body. When we look at these fluids in the human body, we've got them in two main places. We've got extracellular fluid and we've got intracellular fluid. And so we're going to take a look at the fluid outside of the cells, extracellular or ECF, and then the fluid inside of the cells, ICF or intracellular fluid. So we're going to look at this. We're going to talk about how eventually our goal is really to kind of balance the ECF, and then a lot of the ICF just kind of falls in line. And so our primary extracellular fluid is our blood or our plasma in our blood. So fluid balance is a lot of times we're going to talk about blood volume and we're going to talk about blood pressure many times whenever we're talking about balancing fluid, because don't forget that your water storage tank is your bloodstream. You don't have a hump on your back where you just store water like a camel or something crazy. And so that's where we keep it, is in our bloodstream. Now, here's a term real quick that I want to hit: edema. We've mentioned this before. Edema is accumulation of fluid in the tissues. So here, this is an imbalance of fluids in the body. Instead of them being in the proper place in the extracellular, we're going to have way too much in the interstitial area instead of in the bloodstream. And so this is where you retain fluids, and the body starts to look kind of like a memory foam mattress a little bit. Whenever you see edema, you push on it and you can kind of see that imprint staying there for a while. So here again, that's retaining a fluid in the body tissue. So extracellular fluid, let's talk a quick little bit about extracellular fluid. Extracellular fluid, again, is on the outside of the cells. And whenever we think about the fluids on the outside of the cells overall, I didn't list it here. I really kind of messed up there. But the main fluid around the side of cells is called interstitial fluid, right? So we've talked about that all through 210 and 211. Interstitial fluid is the primary is one of the primary extracellular fluids. This is the one that we think about that's truly outside of cells, but the biggest component of our extracellular fluid is our blood or our plasma. So many times when we're talking about balancing the fluid in the blood or the plasma, we're kind of talking about hydration, right? So if we can maintain our hydration, then a lot of these other fluids that it communicates with are going to fall into balance as well. And so that's part of it. If we can balance the blood and balance what's in the plasma, then a lot of times we're going to balance all the rest of the fluids that it communicates with. Now, don't forget, another type of fluid that's outside of cells is lymph. Another one is found in our joints, synovial fluid. Another one's found in our central nervous system, cerebrospinal fluid. We still have some others. We could talk about the fluid in the eyeball, the humors in the eye, vitreous and aqueous humor. We could talk about some of the fluids in the inner ear that I didn't really mention in my 210 class, but the endolymph and paralymph. When we look at extracellular fluid, though, we need to understand that it is higher in quantities of sodium, calcium, chloride, and bicarbonate. Okay, so we got 3 ions that were going to be greater in concentration on the outside of a cell, and these make sense. During nervous actions, we have sodium coming in to stimulate that cell. Calcium comes into the synaptic knob to help force the vesicle to release the neurotransmitter, and so it's an easy one to remember there. And usually sodium and chloride, they like to hang out really close together because we know that as salt, right? Sodium chloride is our table salt. So where we find sodium, we're also going to find is buddy chloride, because this is a positive ion and this is a negative ion. And so they kind of hang out together quite often. Bicarbonate, we're going to see this here in just a second. This is going to come back to our ability to balance pH. So the bicarb being in the blood is going to be a good thing. And we're going to see that we're going to use this bicarbonate to balance pH as we try to transport hydrogens through the body and get them out of the body. Again, we're going to make hydrogens in one place and we need to get them out somewhere else. So that's really what the buffers are doing, is kind of transporting these hydrogens out of the body so that they don't affect our overall pH. Intracellular fluid, or ICF, this is the fluid inside the cells. This is what we've always called cytosol. Back in the day, we used to call this cytoplasm, but then they've kind of redefined cytoplasm to include the organelles plus cytosol, which is the fluid, the primary fluid on the inside of the cells. Now, this is the main fluid in our body. Even though we think about blood, if we cut ourselves, we're not going to see interstitial fluid coming out, intracellular fluid coming out. We're going to see blood out, right? But overall, our cells have 2/3 of our body fluid. So most of the fluid is actually inside of our cells. And again, that's kind of showing us that if we can balance the blood, and the fluid in the cells will balance itself to the point where it needs to be, and that just keeps our whole body's homeostasis in that balance that we need. Now, inside the cells, we're going to see more P's. We're going to see more potassium. Remember, we talked about this as dealing with nervous and muscular kind of reactions. And then phosphates. Phosphates are involved with ATP, so we're going to have that ATP on the inside of the cell. We're also going to have phospholipids. We're going to use phosphates for a lot of different things. On the inside of a cell, we're actually going to use phosphates and proteins as buffers as well. So we're going to pull these guys back out and talk about them whenever we get to the acid-base balance. Again, magnesium, we're going to use this as well in many different reactions. This is used in over 300 different enzymatic reactions, so enzyme kind of processes. So magnesium is important to keep our chemistry going. We just don't talk about it very much. It just kind of helps to catalyze some of those reactions. So here again are our main electrolytes. We see sodium. And don't forget, we've talked about in the past how this is important for muscles and for nervous system to stimulate, to create those action potentials that eventually stimulate the contraction or stimulate another component of the nervous system. Then we also mention that sodium is important for water balance. I've tried to kind of stress that in the past chapter, dealing with the urinary system and how important that sodium is. Water follows salt, and so sodium is the main salt that water wants to follow. So if we can put sodium in one place, then water is going to try to head there to balance itself out. Potassium, we mentioned muscles and nervous system again, kind of working side by side with sodium, or not side by side, but opposite of sodium. Sodium is more stimulating and potassium is more inhibiting whenever these channels are opened, right? And so it kind of causes different types of stimulations. Chloride, again, is going to be used in the nervous system. So chloride is involved sometimes with a hyperpolarization. Chloride's on the outside of the cell, and so sometimes it comes in to trigger that hyperpolarization to make the inside more negative, because chloride is a negative ion. Also involved in digestion. We just finished talking about hydrogen, not hydrogen chloride. So we just finished talking about HCl, hydrochloric acid, excuse me. And so hydrochloric acid is definitely using chlorides as one of the main components of that digestive ability in the stomach. And so HCl, that Cl is that chloride. Calcium, let's don't forget that calcium makes, we store most calcium in our bones, just like the phosphates. Calcium and phosphates tend to be found together whenever they're in storage, and so they tend to be stored in the bone and in the teeth, and these are kind of extracellular in that capacity a lot of times. But then they work inside and outside of the cell a little bit differently. So we just mentioned muscle and nervous, how it stimulates the release of synaptic vesicles and the release of neurotransmitters at the synaptic knob. But we also kind of talked about this back in the day in 211, towards the beginning of the semester, when we talked about clotting and how calcium was one of the clotting factors. So calcium is important for blood clotting. Phosphates, again, kind of mentioned that they work with that calcium as far as storage, and that's really what makes our bone and our teeth, is a lot of calcium phosphate and calcium hydroxide, and that's what creates that hydroxyapatite, right? And that's the main matrix of our bone. So phosphates, let's don't forget that DNA, that any of our nucleic acids are going to have a phosphate and a sugar and another nitrogen molecule, and so that's really what creates a nucleotide. That's what makes our nucleic acids. So phosphates are important for nucleic acids, for DNA, for RNA, for ATP, right? And then we talked about phospholipids, and so they're important for cell membranes. And as I mentioned just a second ago, we're going to use these as a buffer as well. These phosphates can be a buffer for some of our areas in our body, some of the fluid regions. Magnesium, again, we're going to store it in bone, kind of as our trace elements, but it's important for muscle reactions, but also for over 300 other enzyme reactions in the body. Now, whenever we're looking here, I want us to understand that overall, fluid and electrolyte balance, they're going to work together. This is not necessarily mentioned quite as well in the textbook, but I do want you to be aware that there are kind of four main principles that kind of rule the fluid and electrolyte balance. And I just realized that I didn't correct this. I should have corrected this, folks. So make sure that you're realizing blood monitors. What is blood? It's an ECF. So blood monitors respond to ECF. Instead of that ampersand, that should be a not. Okay, so this should read blood monitors respond to ECF, not ICF. So the point is that most of our monitors are dealing with the bloodstream. And so whenever we're looking at fluid and electrolyte balance, we're actually measuring that in the bloodstream. And as I mentioned, we're going to allow the other fluids that are communicating with the bloodstream to kind of fall in line and to balance themselves off of the bloodstream. Now, when we're monitoring the bloodstream, we need to realize that there's no gauges, there's no direct fluid or electrolyte monitors. So what that means is we don't necessarily have a full versus empty when it comes to sodium, when it comes to potassium, when it comes to water. We don't know the concentrations, or we don't know the total amount, the total volume, but what we pay attention to is the osmotic concentration. And so that's what's important, is this osmotic concentration. If you remember, osmotic pressure, osmotic concentration is basically the amount of water in a solution due to the other solutes. And here the other solutes are the electrolytes. So in other words, we're almost kind of monitoring thickness in a way, not really thickness, not viscosity, but we're really monitoring how much electrolytes per unit of water are there. And overall, that's kind of density, that's kind of thickness. And so there's no direct monitors. What we're monitoring is to make sure that it has the correct osmotic concentration, the correct amount of electrolytes per fluid, no matter how much where we're looking at. right? So we're not really looking at total volumes and, oh, well, we need 10 units of this. No, we're just looking to make sure that there's a balance. There's the right amount of electrolytes for the right amount of water, okay? Now, another thing that we've been mentioning over and over is water follows salt. Water moves by osmosis, but what sets up osmosis are the solutes. And here especially, we talk about salt being the primary solute that helps to set this up. Water is going to follow any solute. And so we mentioned that in capillaries, how water follows the proteins, and that's how we got our osmotic pressure, our osmotic potential. And so here, we need to know that water does move by osmosis, but it tends to move to where there's more salt. And this is something that they're going to hammer in your nursing program. You know, if you have a patient in the hospital, you're not just going to give them an IV of water, you're going to give them a saline drip more than likely, because you're going to give them some sodium to help keep that water in. If you just give them water, there's not enough salt in there possibly, and so they're not going to retain that water. And so you need to give them a little sodium most of the time, many of the times, and then that way it helps to keep that water into the body instead of that person just urinating and out. Now, this is really a major thing right here, rise and fall in these two guys. So if we need more fluid body, or we need more electrolytes, then our gains need to be greater than our losses. Our intake needs to be greater than our output. So in other words, if we need to increase the fluid in the body, then we need to increase how much we're drinking and getting into the body versus how much we're urinating and sweating and letting it out. Okay, intake versus output. So fluid in versus if it equals fluid out, then we're in a balance. If we take more in than we take out, then we're over hydrated, or we have over amount of electrolytes. And then the opposite is true. If we let more out than we let in, then we're dehydrated, or we are at a deficit. We're hypo for these electrolytes. Now, there are four main hormones that are going to really kind of get this thing going. And whenever we look at these hormones, these are, again, we've talked about these whenever we talked about hormones in the heart and the bloodstream. There's two real main players in the middle, ADH and aldosterone. Don't forget ADH, it is from the post-pit, but it conserves water. In other words, it's going to affect the gains and the losses. It's going to trigger you to lose less and to drink more, right? So it's going to stimulate your thirst center, and it's going to lower how much water loss is at the kidneys. It's going to keep it in. And we talked about that, how alcohol can block ADH, and then it causes you to urinate excessively, right? So ADH keeps the water in. Aldosterone from the adrenal cortex is one of our corticosteroids. It keeps the sodium in. It keeps the electrolytes in. It lets some of the potassium out. A lot of times we're at an excess of potassium, so here's a place that we can lose it. Sometimes we're not, but a lot of times we are. And so we're going to conserve it if we don't have enough, and we'll let it loose if we've got too much. Generally, we always want to conserve the sodium. And again, these are some of our electrolytes. So aldosterone conserves electrolytes, keeps them in the body. ADH keeps water in the body. So these are the two main players, right, for our water balance. If we turn them on, well, then we get more gains than losses. If we block them, then we get more losses than gains. And that's kind of how these other two hormones are going to control them. Renin is going to trigger a series of hormones, and eventually the end is going to be one called angiotensin. Angiotensin, blood vessel tension, that means it's going to increase blood pressure, right? This is made at the kidneys, and angiotensin is going to increase blood pressure, and how we do that is increasing blood volume. We're going to increase the gains and decrease our losses. So that means we're going to stimulate ADH and aldosterone. That's one of the main ways that this achieves that ability to keep that blood pressure up and to keep that volume in, is to trigger more ADH to keep the blood in, and trigger aldosterone to keep more salt in, so that the fluid stays in the blood. So here, renin and angiotensin, they up-regulate ADH and aldosterone. They stimulate them. On the other hand, if we've got too much blood volume, or our blood pressure is too high, then the heart's going to stretch, and it's going to make atrial natriuretic peptide, ANP. And so when it makes this ANP, that is going to block ADH and aldosterone. If we block ADH and aldosterone, it's going to decrease our thirst, but it's also going to increase our water loss at the kidneys. And so that's going to increase urination. So if we can go pee out some of that excess water that's been in our bloodstream, then we can drop the volume and we can drop the pressure. And we're going to do that by blocking ADH, similar to alcohol, and blocking aldosterone so that there's less sodium to keep the overall balance, the overall osmotic balance. So 4 hormones, there's really 2 players in the middle. Renin-angiotensin stimulates, AMP inhibits these other 2 in the middle. Now, here are just a couple of things that I've mentioned. Overhydration, obviously, if you're overhydrated, then you've got too much water, and that means you're going to start being low in some of your electrolytes. So here, hyponatremia, this is too little, right, below. Natreme is where we get Na, sodium, and so not enough sodium. So overhydration can lead to not enough sodium, hyponatremia, and dehydration can lead to too much sodium compared to the water because you've lost the water, and so now you've still got too much sodium, hypernatremia. Now these guys are on page 1012 in our textbook, so I would like for you to read through these and just make sure that you're familiar with all of the different types of electrolyte imbalances in the blood. And so we've got hyper and hyponatremia, hyper and hypokalemia, and that's what we see here. K, dealing with potassium, so too much potassium or not enough potassium. This is going to throw some things off, so you can kind of see that. And then we have hyper and hypochloremia, and so that's dealing with our chloride. Hyper and hypocalcemia, that's dealing with our calcium. And then hyper and hypophosphatemia, so that's dealing with too much or too little phosphates. And then hyper and hypomagnesium, and so that's dealing with too much or too little magnesium. So all we're doing is taking really kind of the Latin root word and adding hyper and hypo, and that's describing too much or too little. Now, I'm not going to make you know all of the different problems, the causes, the effects, the symptoms that are listed on that chart. I just want you to be familiar with those terms, and because we know the function of some of these ions from that previous page, from one of those previous pages, we can kind of estimate what some of our issues might be. If we don't have enough sodium and potassium, we're going to have some nervous issues, right? We're going to have whatever those we're functioning for. Now we're going to have some problems, all right? So take a look, page 1012, and that's table 25.1. Let's move on. That kind of wraps up our fluid. Let's move on and talk about acid-base balance. This is complicated, but we don't have very much information that we're going to cover here, so that makes it a little bit easier. A buffer system. Don't forget that buffers are a substance that can resist a change in pH. So a buffer, if we have an acidic solution and we add a buffer, then it's going to take that acidic solution and take it back up towards 7, back towards our middle ground, our neutral, where we want to be. And so buffers, really what they're doing in our body, and this is really kind of the important kind of thing that they're truly doing, not just a technical definition, but they're transporting hydrogens. They're binding and releasing hydrogens throughout the body so that they don't affect our overall pH. So in other words, a buffer is a chemical that can bind and release hydrogens, but when it binds and releases these hydrogens, that chemical is not affected. Many chemicals, if we bind and release hydrogens from it, we're going to split those things apart. We're going to break them apart. That's why the pH causes trouble. But there's some molecules like proteins, amino acids, and carbonic acid bicarbonate, and some phosphates that we can use as transports for hydrogens. Now here's the key. Inside the cells is kind of where we're going to start making these, right? This is where we have most metabolism, is inside the cell. So here in the ICF, we've got 2 systems. We've got the phosphate system and the protein system. And if you remember, those were 2 things that were higher there on the inside of the cell, were protein and phosphate. So we're going to use those to help buffer this pH. So they're going to bind them once they're made, and then they're going to take them and they're going to pass them on to the ECF. Now we've got two that are working the ECF, the protein buffer system in our bloodstream. We can use proteins. And we can also use bicarbonate, and carbonic acid is what it's going to become, but bicarb is the real buffer. So we can use bicarb and proteins in the ECF. Now I want you to know that the primary one that we're going to use is this carbonic acid bicarbonate buffer system. That's the reason that I've got this equation right here, to know this equation, and I'll talk about it here in just a second. Now, once we balance in the blood, then the biggest issue is getting it from the blood out of the body. And so that's what we're going to do through urine. We can simply just add these H's into the urine. We've got phosphates that we're going to urinate out, and so we can bind the H's to the phosphates so it won't affect the pH of the urine. And so in the urine we've got phosphates, and that's kind of getting these guys out. So there is one way. You've already learned one way that we can fix a pH imbalance is simply by adding more hydrogens or less hydrogens to the urine. And if we tinkle those hydrogens out, then that brings us back up in pH closer to our neutral of 7. And if we don't let as many out, if we're in a higher pH, that can drop it. Okay, don't forget, pH is the measure of hydrogens. And something that we've already talked about is that as you increase in the number of hydrogens, the pH decreases, right? So more hydrogens equals a lower pH, okay? Now don't forget also our pH scale is from 0 to 14, and 0 to 14 is kind of flipped. The 7 is in the middle, and that is neutral, but then below 7 is our acidic area, and don't forget that means that we have more hydrogens. Look right here at this equation. Right here's our hydrogen. This is a free floating hydrogen, and this is what we're measuring. We're not measuring this hydrogen right here that's bound to another molecule. We're measuring a hydrogen that's all by itself. And the big problem is this thing can bind to many different other molecules and split them apart, as I mentioned a second ago. And so these hydrogens are really our concern with pH. Too many of them, we're acidic, and not enough, we are basic or we're alkaline. And in the long run, we need to be somewhere around 7.35 to 7.45. That's an important range. That's the main range of a balance for the human body is 7.35 to 7.45. 7.4, a little above, a little below. That's the way to think about it. And so these hydrogens, again, they're free radicals that can cause unwanted reactions. So we need to bind them up in the body so they don't break down our important stuff, and then find a way to get them out. And there, again, we found a way. It's through the urine. Now let's look at this equation real quick, and let's notice something. Over here is our hydrogen, right? So there's the hydrogen. That's our problem. And this molecule right here is bicarbonate. HCO3 minus is bicarbonate. So you need to know that. Bicarb, what it does is it binds up this hydrogen and it takes it out of the fluid so it doesn't affect pH anymore. And that's what buffers do, again, is they bind hydrogens without changing and becoming something bad. So when we bind it up, we make this molecule called H2CO3. H2CO3 is carbonic acid. So you should know that. This is carbonic acid. Carbonic acid can then dissociate. And again, we see these arrows going both ways. That means that we're going to hit a balance. If we've got too much of one thing on either side, either CO2 or hydrogens, then we're going to balance over to the other side. So we can affect pH by either having too many hydrogens made in a cell or by affecting the CO2 levels in the blood. And this is something new, because this H2CO3, it disassociates and it becomes CO2 plus H2O. And a lot of times this is where we start out with, though. And I mentioned this back in the blood chapter, that the main way that we carry carbon dioxide in the bloodstream is in carbonic acid. So while we're transporting this carbon dioxide, we're also using it as a buffer to transport hydrogens. And so now we're doing two functions of the same molecule without any negatives at all, really. And so this is two positive functions that we're getting from this H2CO3, this carbonic acid. It's acting as a buffer. It's helping buffer this H, but it's also transporting this hydrogen. But now what that tells us, through this system, the main system that we're going to learn, we have two places that we can affect pH. With these H's, we can affect these. At the kidneys, we can simply add them into the urine and then let them out of the body, and we can raise pH. We could also mess around with bicarbonate, because if we don't have enough bicarb, then we've got too many H's, so that can lower pH. If we've got too much bicarb, we don't have enough H's, and that can increase pH. And so when we look at these H's right here, this is our real problem. The more of these we have, the more acidic we become. And right here, you need to know we can adjust that directly at the kidneys. Now, on the other side, we have CO2. CO2 is something that we can control with our breathing. So we can change our breathing rate. We can hold our breath. We can breathe faster. That means we can leave more CO2 in or let more CO2 out. And the key is, if we increase the CO2 in the body, everything else increases in this equation. So the hydrogens go up too. So I want you to know that more CO2 in the blood makes it more acidic. It lowers the pH. So CO2 and hydrogens are directly related. If one goes up, the other goes up. But remember, as our hydrogens go up, the pH does the opposite. It goes down. And so CO2 can become hydrogens as well through this entire equation. So we can also solve a pH problem at the lungs, though. By breathing faster or breathing slower, we affect how much CO2 is in the blood, and then that affects how much hydrogen is in the blood. So we've got two places. We've got a respiratory mechanism, and we've got a renal mechanism for taking care of this pH problem. Now, let's take a look again. And I've kind of mentioned this already, and we don't have very much more dealing with this acid base. We're going to wrap it up fairly quickly. Again, I want us to only learn the bicarb carbonic acid system. And so again, we've got CO2 plus H2O gives us carbonic acid. We take away the hydrogen, and we've just got the rest of it, HCO3. And so there's our acid problem, and here is our bicarb, which is our actual buffer. So I want you to understand, first off, renal compensation. I mentioned this. We can change something on this side to affect at the kidneys. To change pH by simply keeping or letting more hydrogens out in the urine, or keeping or letting more bicarb out in the urine. Again, if we keep the hydrogens in, we lower pH. If we let the hydrogens out, we increase pH. If we keep the bicarb in, then we're going to bind more hydrogen, so that means we're going to increase pH. And if we let more bicarb out, then that means we're not going to be binding as many hydrogens, and that means we're going to decrease pH. So we can affect either one of those at the kidneys by simply keeping them in, reabsorbing them, or secreting them into the renal tubules, into the tubular fluid that's going to become urine. Now, the respiratory is a little more complicated. I mentioned this just a second ago. CO2 and hydrogens are directly related. So if we increase CO2, we also increase hydrogens. So more CO2 equals more hydrogens equals lower pH. So if we drop the pH, now we got some problems. Now, in order to fix the problem, so we've got too much CO2 in the blood because we're not breathing fast enough to begin with. So if we're not breathing fast enough, that means we're not getting rid of the CO2 fast enough. So that means it increases. So when the CO2 increases, more CO2 equals more hydrogen equals lower pH. Now, the solution, and these arrows right here should be, the solution is to breathe faster. If we breathe faster, hyperventilate, then we're going to be able to get rid of that CO2. We're going to increase the CO2 loss, and that's going to bring our pH back into a balance. So again, if we've got too much of this, we got too much hydrogens. And in order to bring them back down, we need to decrease how much CO2 is in the blood. So we got to breathe faster to get it out of the bloodstream. And that's going to decrease those hydrogens, and then that's going to fix that pH problem. The opposite is true if we don't have enough CO2. If you're hyperventilating and breathing too fast, then you're not going to have enough CO2 in the body. And then that's going to create an alkalosis. That's going to create a basic condition in the bloodstream. And so alkalosis means high pH. Up here, acidosis meant low pH. So here, to fix the alkalosis, the high pH, we need to breathe slower. We need to retain. We need to decrease the amount of CO2 that we're losing, and then that's going to keep it in our bloodstream, and then that can affect the pH and bring it back down to normal. So here is our respiratory mechanism. We can breathe faster or breathe slower to create the problem, and then we do the opposite to fix the problem. That's basically the way it works. Okay. Now, here are some acid-base disturbances, some balance disturbances, and this is the last thing that we're going to take a look at here today. These begin on page 1024 in your textbook, and they're really discussed in detail on page 1025 and 1026 overall. Okay, so if you flip over there, I'm just going to kind of repeat a little bit of what they've got going on that they're talking about there. Acidosis is generally the biggest problem in the body, and so we're going to see more issues with acidosis than we see with alkalosis. And again, acidosis means that the pH of the body has dropped too low, and alkalosis means that the pH has kind of risen too much. So first off, respiratory acidosis is the most common acid-base balance disturbance. And so this is our most common disturbance. Is due to breathing, we are going to create an acidic situation in the bloodstream. So hypoventilating, sometimes dealing with breathing, some people may have injury or some sort of effect due to a drug or a disease that could affect the breathing rate, and so decreased breathing, decreased airflow. So obviously if you're choking, or if you have bronchitis, or if you have severe asthma, then you're going to have more acidic blood if you're not getting that air exchange as efficiently as you can, because that CO2 is building up, right? And then also impaired alveolar gas exchange. So if you have a problem with exchange at the alveoli, well, then we're going to see it here in respiratory acidosis. Let's go ahead and let's hit respiratory alkalosis while we're here. Okay. Again, alkalosis is not very common. Alkalosis is due to hyperventilating overall. So if you're breathing too fast, then you're eliminating too much CO2. So severe anxiety could be a problem, or hypoxia, insufficient oxygen to the body. Aspirin overdose could actually cause alkalosis. And so the whole key, if you're hyperventilating, you're losing too much CO2, and that means that you don't have enough hydrogens in the body. And so the key is to breathe into a bag, right? Because that bag is magic. No, the bag is not magic. What you're doing is you're rebreathing the CO2 back into your body, and now your low levels of CO2 start to rise back up. And so that's the reason if somebody's hyperventilating, they give them a bag to breathe into, because they rebreathe their own CO2, and then that starts to fix that issue. Now, metabolic acidosis is the most common of the metabolic disorders, and the second most common of these disorders overall. So again, metabolic acidosis, either you're making too many acids, so there is an accumulation of too much acid in the body. So for example, ketoacidosis, that could come about from some dieting or diabetes, lactic acidosis from too much exercise. Acetic acid is made from the breakdown of alcohol. So if you have too much alcohol in the system, then you could have acetic acidosis. And so these things can affect it. It could also be due to too much stomach acid. So if you are making way too much stomach acid, or maybe you're losing too much bicarbonate, and then it's going to end up dropping that acidity due to metabolism. Now the last one is metabolic alkalosis, and this one's fairly rare in comparison. And so this is due to losing too much acids overall. So for example, vomiting, you're going to lose way too many of those stomach acids, and that's eventually going to affect the overall pH of the body. It could be due to kidneys on diuretics. Maybe you've have lost too much hydrogens due to a diuretic, and you've got too much bicarb, and so you're binding way too much up. So definitely not a good thing. If you overdose, not overdose, but if you take way too many antacids, then that's something that can trigger that as well, because an antacid is going to cause alkalosis, right? It's against the acidity. So that kind of wraps it up today for our balances chapter. Not very long, very basic. And I want you to make sure that you get a good understanding of the basics, because when you get to your program, they're really going to hammer those details that you need. So I don't want to get in too much detail in this chapter. And plus, we're kind of winding down the semester, so I don't want to overwhelm you guys. If y'all have any questions, please feel free to get them ready for the lecture or hit me over email. All right. Have a great afternoon.